Thank you. Thank you for the presentation, and thank you for inviting me today. And a special thank to Guillermo that is taking care of me here during these days. Well, the title of this presentation is Characterization of Organic Aerosol Sources and Atmospheric Processing. As we said, I work in Bologna, but I'm from Milan in northern Italy. So I'm presenting here a couple of pictures taken from Milan, the skyline of the city. Here was during a sunny and summer day, clean day, PM 2.5 concentration was 5 micrograms per cubic meter. This is the same kind of skyline taken from a winter and a polluted, very polluted day. And PM 2.5 concentration was 71 micrograms per cubic meter. So as you can see, the aerosol is able to absorb and scatter visible light. And the result is this, it's very clear. The ability to absorb and scatter solar radiation makes the aerosol able to interfere and contribute to climate change. Atmospheric aerosol is also important for the impact on human health. In fact, the World Health Organization calculated that every year about 3.7 million premature deaths can actually be attributed to exposure to air pollution. So the annual mean concentration of PM 2.5 that should not be exceeded in order to avoid damages for human health is 10 micrograms per cubic meter, according to the World Health Organization. So you can see here that we can actually be much, much higher than that. This map shows the annual PM 2.5 average concentration estimated from satellite images. As you can see here, the concentration varies from less than 1 micrograms per cubic meter up to 80 micrograms per cubic meter. The highest concentration are observed, for example, over the Saharan region, and this is mainly due to natural sources, the resuspension of soil, of dust. But then we have very high concentration in regions affected both by natural and anthropogenic sources, like the East Asia and South Asia, and then again, quite high concentration in Europe. This is the Po Valley, and you can see that it's this orange-red spot there. And also Mexico City is here. So you can see an orange spot here as well. So as we said, the limit is 10, so we should be around here. And you can see that there are a large part of the world where a large number of people live, where the concentration is much higher than the limit set by the World Health Organization. So about 86% of the global population is actually exposed to PM 2.5 concentration well above this limit. Well, organic aerosol is a mixture of different chemical species. This figure is taken from a quite old now study that collected different aerosol mass spectrometer measurements taken in different parts of the world during different field experiments. And the pie charts here show the average composition of fine particles. So you see that fine particles, this is PM1, are mainly composed by sulfate in red, nitrate in blue, ammonium in orange, and then we have this, it's supposed to be green or yellowish slice, which is organic aerosol. So organic aerosol is responsible for a large fraction of fine particle mass that can go from 20 up to 70% of fine particle mass. Usually we expect high contribution of organic aerosol in rural areas, like for example in the forest in Finland, or also Canada here at Chibok Point, because in rural or forest areas we have large emission of volatile organic compounds, which can be oxidized and form organic aerosol. But it's interesting here to note that we have very high concentration of organic aerosol also in urban environments, for example here New York City, as well as Mexico City, this one. Organic aerosol is a mixture of thousands of different chemical species. So while at the beginning researchers were trying to characterize organic aerosol, identifying the different chemical species, During recent years, the aerodynamic research has developed this instrument, the aerosol mass spectrometers, that give us the possibility to describe in a simplified way the organic aerosol. In this kind of instrument, essentially, we measure the aerosol composition online. So the aerosol particles are sucked into the instrument. They are first passed through an aerodynamic lens, so they are focused into a narrow beam. Here, they pass into 2 different chambers, and then they reach this oven. The oven is heated at 600 Celsius, so when the particles hit the oven, they vaporize. In the same region, we have a filament that emits electrons at 70 electron volts. So when the gas molecules hit with the electrons, we have the ionization. The ions are then focused into this mass spectrometer chamber, is a time of flight chamber. And so depending on the mass to charge ratio, they follow this path in different time. And so we are able to reconstruct the mass spectra of the particles that get into the instruments. What we are looking at now is the organic aerosol mass spectra. So since this instrument works online, we are able to measure the organic mass spectra, let's say every minute or 2, or what we do usually is 5 minutes. And we get one spectrum like this. Then, during a field experiment that might last for 2, 3, 4 weeks, we collect thousands of spectra. To analyze them, you use the multivariate statistical analysis. Usually, we use the positive matrix factorization kind of analysis that allows us to identify the different sources of components of the organic aerosol. So here, this is the same study that I show you below. And they apply the positive matrix factorization analysis to identify the different components of the organic aerosol. And in a very simplified description, we can describe the organic aerosol as composed by 2 components: the hydrocarbon-like organic aerosol, which is mainly related to primary emission, fresh aerosol, and oxygenated organic aerosol, which is mainly a proxy of secondary organic aerosol. And what is extremely interesting here is that, okay, in rural and remote sites, the secondary organic aerosol dominates over primary. But this is true also for urban downwind and urban environments, where the secondary organic aerosol accounts for more than 50% of the organic aerosol mass. The same results have been observed also in Europe, more recent years. These results were collected during the Eukarya experiments. During the Eukarya project, we have been able to use different aerosol mass spectrometers at the same time in different places, urban and rural sites, and during 3 different experiments: spring, fall, and again spring 2009. And what they have seen here is that, again, we have a fraction. I'm sorry, but it seems something went wrong, and we don't have the axis labels, but here goes from 0 to 100% for all the axes. And each bars correspond to a different site. And what they have been able to observe is that organic aerosol is composed by an hydrocarbon-like organic aerosol factor. So again, related here, the hydrocarbon-like organic aerosol corresponds actually to traffic emission. A brown bar corresponds to the biomass burning organic aerosol. That here is organic aerosol emitted from wood burning for residential heating in fall, or agricultural waste burning in spring season. But then again, also in Europe, the oxidized organic aerosol, so the secondary organic aerosol, accounts for the largest fraction of the organic aerosol mass, both during spring, but also during the cold season. So what we can conclude at this point, so the implementation of effective policy measures to reduce PM concentration is mandatory, because we want to reduce the adverse health effects associated with exposure to air pollutants. So far, traditional measures focus mainly on primary emission, but with only local and short-term effects. So most effective measures now should focus actually on secondary aerosol, and here especially on secondary organic aerosol. In a traditional representation of secondary organic aerosol is formed from gas phase molecules, which are oxidized in the atmosphere in the gas phase, to produce new molecules, which are characterized by a lower volatility compared to the precursors. So the new product can condense on pre-existing particles, adding mass to the organic aerosol. Using this kind of representation, Kanakidou et al. 2005 estimated the global secondary organic aerosol budget that should range between 12 and 17 teragram per year. So around 40, the average, the middle point. Then later, Held et al. And Ahlquist et al. 2009 tried to estimate the global budget for secondary organic aerosol, now using observation. So observation of secondary organic aerosol in the troposphere, at the ground, but also using satellite image. And what's interesting that they actually reached similar results, and they concluded that the global budget of secondary organic aerosol should actually range around 250 teragram per year, which means that there is a large discrepancy between what observations are reporting and what actually models are able to predict. So during the last 3 years, I would say, a few researchers have started thinking that maybe there are new mechanisms for the secondary organic aerosol formation that models are ignoring. And one of these mechanisms is the formation of secondary organic aerosol in the aqueous phase. In this case, we have organic molecules in the gas phase, or also organic molecules in the particle phase that can dissolve in atmospheric water. Atmospheric water can be the water absorbed on aerosol particles, but also the water in fog droplets or cloud droplets. Once in the aqueous phase, these organic molecules can actually react to form new organic molecules, which have a lower volatility compared to the precursor. And so when water evaporates, they remain in the aerosol phase, forming aqueous secondary organic aerosol. And that's the way we call it, aqSOA. So the question we want to answer with this work are, what are the conditions necessary? So when the aqueous secondary organic aerosol can actually the formation of aqueous secondary organic aerosol can actually be important. What are the precursors, and what are the mechanisms that lead to the formation of these species? To answer this question, we use data collected in the Po Valley. The Po Valley, this is a map of Europe. This is Italy, and the Po Valley is here, is in northern Italy. It's surrounded to the north by the Alps and to the south by the Apennines. So we have a population of 20 million people over the entire valley and a surface of 47,000 square kilometers. I report here also the average, the annual average PM2.5, which range in the urban areas between, but I have to say there are not big differences between urban and rural areas here. And the PM2.5 ranges between 25 and 30 micrograms per cubic meter, which is definitely higher than the limits set by the World Health Organization, but is also higher than the limits set by the European Air Quality Directive, which is 25 micrograms per cubic meter. So the first time we observed the formation of the aqueous secondary organic aerosol was actually in fog water. The Po Valley is often characterized by dense fog events during the winter and fall. This is a satellite image that shows, for example, a dense fog event that is actually covering the entire Po Valley. So you see here the Alps and the Apennines here. During one of these cold seasons, specifically in fall 2011, at the rural site of San Pietro Capofiume, which is here, we have been able to measure the organic aerosol properties online using an aerosol mass spectrometer. And at the same time, we sampled fog water here. You see the fog water samples. We collected a lot of fog water, and they are actually very dark, so very polluted area. So we took the fog water samples back to the lab. we aerosolize them, and we analyze the organics dissolved in fog water using another aerosol mass spectrometer. And this is the average mass spectrum of the organics dissolved in fog water. What you see is that the highest peak are pink. So the pink peaks corresponds to fragments that contains oxygen, oxygenated fragments, and are typical of processed organic aerosol or secondary organic aerosol. The most intense peaks are at MZ29, which is CHO+, MZ44, CO2+, and MZ43, C2H3O+, which for those that are familiar with this kind of instruments, these peaks are very typical of oxidized organic aerosol or secondary organic aerosol. And what is particularly interesting here is the importance of this peak at MZ29, which is usually observed in oxidized organic aerosol in cloud droplets. The bottom spectrum is actually the mass spectrum of the oxidized organic aerosol observed in San Pietro Capofiume right after fog evaporation. So we know how the organics in fog water look like, and this is the organic aerosol that we see when fog disappears, when fog evaporates. And you see that the two spectrum are actually very similar, look very similar, with the most intense peak at MZ29, 43, and 44. So we concluded that this oxidized organic aerosol observed after fog dissipation was actually originally present in fog droplets, so remains in the air after fog evaporation, and we think is actually formed in fog droplets. So we think this is actually aqueous secondary organic aerosol formed from fog processing. We were actually able to observe the aqueous secondary organic aerosol not only in fog water, but also in aerosol liquid water. And this was in Bologna at the urban site during a different field experiment. Bologna is an urban site, so we have this heat island during winter, meaning that usually in the urban area we don't see fog events, but still we have very high relative humidity. And the aerosol in the Po Valley is very rich in secondary inorganic aerosol, so it's also very hygroscopic. So the aerosol particles are able to absorb water, and so we have very humid and wet particles. And so during this experiment in Bologna, we measure the organic aerosol properties with an AMS, and then we identified the different organic aerosol component using, again, the positive matrix factorization analysis. And these are the results. Very quickly, on the left axis, the time trends of the different components, and on the right side, the mass spectra of the different components. So we were able to identify a hydrocarbon-like organic aerosol component, which relates mainly to traffic, a biomass-burning organic aerosol, which is mainly related to the use of wood burning for residential heating, and then 3 different kinds of oxidized organic aerosol or secondary organic aerosol. But I would like to focus your attention on this one, this oxidized organic aerosol type 3, that we think, and I'm going to show you, it's aqueous secondary organic aerosol. Here again, the time trend of this oxidized organic aerosol 3 and the corresponding mass spectrum. So the concentration of this component varies from less than 1 micrograms per cubic meter up to almost 10 micrograms per cubic meter. So its concentration is important. Remember that 10 is the limit that we don't want to exceed. How did we say that this is actually aqueous secondary organic aerosol? Well, we use a tracer of aqueous phase chemistry, that is this hydroxymethan sulfonate. Hydroxymethan sulfonate is this molecule. This is formed only in the aqueous phase from the reaction of formaldehyde dissolved in water with the sulfide ions, which is formed from the SO2 that dissolves into the water. This molecule is characterized by a low volatility, so when water evaporates, it remains in the aerosol phase. And we're actually able to measure it using the aerosol mass spectrometer. This time trend actually is the hydroxymethyl sulfonide time trend measured during the experiment. And you see that there is a very good correlation between the two time trends here. The second evidence that this oxidized organic aerosol is actually formed in the aqueous phase is the mass spectrum. So this is the mass spectrum of the aqueous secondary organic aerosol. And again, as before, the most important peaks are at MZ 29, 43, and 44. And this is the organic mass spectrum of the aqueous secondary organic aerosol formed from fog processing. Another important point is the oxygen to carbon ratio. So the aqueous secondary organic aerosol formed in Bologna and so in wet particles has an oxygen to carbon ratio of about 0.6, which is similar to the oxygen to carbon ratio observed for the aqueous secondary organic aerosol formed from fog processing. Well, during smoke chamber experiments, when we try to reproduce the secondary organic aerosol from the oxidation of gas phase molecule into the gas phase, we obtain secondary organic aerosol that have an oxygen to carbon ratio between 0.3 and 0.4. So only when we try to produce secondary organic aerosol in laboratory in the aqueous phase, we can reach value that range between 0.6 and 0.7. So this elemental composition is confirming our hypothesis that this is actually aqueous secondary organic aerosol. Finally, as I said before, in Bologna, we did not have fog events, so we think that the aqueous secondary organic aerosol is formed in wet aerosol. So using the extended aerosol inorganic model, we simulate the aerosol liquid water content during the experiment, and we see that the aqueous secondary organic aerosol correlates quite well with the aerosol liquid water content, confirming again that the aqueous phase is the medium where this secondary organic aerosol is formed. I just want to point out that the highest concentration are observed in this period when the temperature is usually below 5 Celsius and relative humidity is higher than 70%. So to answer the first question, what are the conditions ideal to form aqueous secondary organic aerosol? We observed this formation in fog droplets, but also in aerosol liquid water, when temperature was low, below 5 Celsius, and high relative humidity. We need low temperature because we need gas phase precursors to dissolve into the aqueous phase. And for the Henry lower temperature, we have higher solubility of gas phase species. So the next question is, what are the precursors? Well, we know that in the Po Valley, one important source of pollution is wood burning for residential heating. And we know that wood burning actually emits a large number of molecular species, including, for example, phenols, like these ones, the guaiacol, acids like manilic acids, sugars like levoglucosan, mannose, and galactosan, and aldehydes like the metacrolane or formaldehyde. Well, most of these species are actually water soluble, so that potentially they can contribute to the formation of the aqueous secondary organic aerosol. And what is interesting in that is that during the last years, few researchers have proved that some of these molecules can actually form aqueous secondary organic aerosol. For example, aqueous secondary organic aerosol was formed from the oxidation of levoglucosan, but also from the oxidation of phenols like guaiacol or syringol. For example, the oxidation of guaiacol in the aqueous phase leads to the formation of this dimer. The guaiacol dimer is emitted also during the, as a primary pollutant during the combustion of wood. So guaiacol dimer is seen as a primary pollutant, but is also a marker for aqueous secondary organic aerosol. And the good thing is that the guaiacol dimer can actually be detected with the aerosol mass spectrometers that we used. And we were able to detect the guaiacol dimer, both in San Pietro Capofiume, so for aqueous secondary organic aerosol formed from fog processing, but also in Bologna, so for the aqueous secondary organic aerosol in wet aerosol. This graph shows the guaiacol dimer signal measured with DMS versus the primary biomass burning organic aerosol, again measured with DMS. And markers are color-coded as a function of the aqueous secondary organic aerosol. So here I reported only points corresponding to very low, negligible concentration of aqueous SOA. So when this kind of, the formation of this SOA was actually inhibited. And you see that there is a good correlation, and the points actually follow on this line, which corresponds to the guaiacol dimer that we expect from primary emission. Now I add all data points, so also when we observe the formation of aqueous SOA, and you see that when the aqueous secondary organic aerosol formed, for example, light blue, green, yellow, and red points, the guaiacol dimer concentration is higher than what is expected solely by the primary biomass burning. The same is observed also here in San Pietro Capofiume. After fog dissipation, these are the points. And again, we see that when aqueous secondary organic aerosol formed, we have guaiacol dimer higher than expected solely from primary sources. So there is a link between the aqueous SOA formation and biomass burning. To make stronger the link between aqueous SOA and biomass burning, we use the Cubison et al. Kind of graph. This diagram reports on the y-axis the F44, on the x-axis the F60. Well, F44 is the ratio of the signal measured by the AMS at MZ44, normalized over the organic aerosol concentration. And F60 is the intensity of the signal measured at MZ60 by AMS, normalized over the organic aerosol concentration. Well, MZ44 corresponds to CO2 plus fragments, which is typical of oxidized, processed, aged organic aerosol. MZ60 is formed from the fragmentation of levoglucosan and the other anhydrous sugars emitted during wood combustion. So F60 is a tracer of fresh biomass burning. So what we expect to see is that fresh biomass burning following this region of the graph with high F60 and very low F44, because it's fresh aerosol. But then, when the biomass burning organic aerosol aged in the atmosphere, we expect that the levoglucosan, for example, is oxidized, and so the F60 is supposed to decrease. But at the same time, since the organic aerosol bulk is oxidized, we expect an increase in the F44 signal. So the aged biomass burning should follow in this region. In addition, literature studies show that when there is no influence of biomass burning at all, the F60 follow in this region. So F60 is below 0.003. Here I report the biomass burning and aqueous SOA observed in San Pietro Capofiume, so from fog processing. And we see that biomass burning organic aerosol follow where we expect it to be. And also we see that the aqueous secondary organic aerosol actually shows an influence of biomass burning and looks like an aged biomass burning organic aerosol. And also the same is true for the aqueous secondary organic aerosol observed in Bologna and so formed in wet aerosol particles. So the questions, what are the precursors? We know that gas and aerosol species emitted from wood combustion are contributed to the formation of the aqueous secondary organic aerosol observed in the Po Valley. The last question is, what are the mechanisms, the chemical mechanisms? To answer this, we use the Van Crevelen diagram. The Van Crevelen diagram is used to study the evolution of organic aerosol, both during field experiments, but also laboratory experiments. And it reports on the y-axis the hydrogen to carbon ratio, and on the x-axis the oxygen to carbon ratio. So you see that for Bologna, the light blue triangles, when we go from fresh biomass burning to the aqSOA, aqSOA, we have an increase in the oxygen to carbon ratio, while the hydrogen to carbon ratio remains almost constant. In San Pietro Capofiume, so the green circles, when we go from biomass burning, fresh biomass burning to aqSOA, there is an increase in the oxygen to carbon ratio, but also a decrease in the hydrogen to carbon ratio. So what this diagram is telling us is that the formation of aqSOA in wet aerosol and in fog droplets is likely following different chemical mechanisms. Well, the line that connects fresh biomass burning organic aerosol to aqSOA in fog droplets has a slope of about -1. In this kind of diagram, a slope of about -1 corresponds essentially to the replacement of 2 hydrogen atoms with 2 oxygen atoms, which chemically translate in the formation of a carboxylic acid groups. And this result is actually in agreement with what we expect from the models. In fact, according to the models, in cloud and in fog droplets, the oxidation of organic aerosol is mainly driven by the OH radical reactions. And the main product of OH radical oxidations in the water phase is carboxylic acid groups. Then the line that links the biomass burning OA to the aqueous secondary organic aerosol instead has a slope of about 0, so it's not negative. And this indicates that in the wet aerosol, the formation of a carboxylic acid group is less likely than in fog droplets, which actually makes sense because if you think of a fog droplet, the size of a fog droplet is about 10-20 micrometers. The size of a wet aerosol particle is about 2 micrometers, at least the particles that we are looking at this moment. So it means that in the wet aerosol, we have much higher concentration of solute than in fog droplets. But if you have high concentration of organic aerosol in a wet aerosol particle, it means that you are consuming the OH radical very quickly. So since you are consuming OH radical quickly, OH radical is not able to drive the oxidation of organic aerosol, and other chemical mechanisms are kicking in. The mechanisms that have been proposed in literature are dark chemistry reactions. That means reactions that do not need photochemistry radical formation, but reaction that might lead to the formation of carbon-oxygen bond, carbon-nitrogen bond, and carbon-sulfur bond. One way to investigate what was actually going on in the Po Valley, here I reported a couple of examples of dark chemistry mechanism. For example, in literature, it has been suggested that aqueous secondary organic aerosol can be formed from glycol. Glyoxal. Glyoxal in the aqueous phase is hydrated. Then the hydrated form can actually react with the glyoxal itself to form this kind of dimer. And you see that in this way we form new OH groups and also carbon-oxygen-carbon kind of structure. This kind of reaction is a hydration and oligomerization reaction. Another kind of dark chemistry reaction is the nucleophilic addition. In this case, you have the glyoxal, but you can actually have other aldehydes of ketones. And then the carbonyl groups react with the alcohol group to form this new structure with carbon-oxygen-carbon bond. To try to understand what was actually going on from a chemical point of view in the Po Valley, we analyzed the aqueous secondary organic aerosol using the nuclear magnetic resonance spectroscopy. And here report the composition in terms of organic functional group for the aqueous secondary organic aerosol formed in fog droplets in green, and the aqueous secondary organic aerosol formed in wet aerosol in blue. And the main differences are that in the wet aerosol, we see this group, the oxygen-carbon-oxygen moieties. And also we have a higher contribution of the carbon-OH group, which is actually in agreement with the products of dark chemistry reaction. We have OH, and then again carbon-oxygen-carbon, OH, and carbon-oxygen-carbon. So we can conclude that the OH oxidation is the mechanism that is mainly driving the organic aerosol oxidation in fog droplets, while in wet aerosol particles, other reactions might be more relevant, including hydration, oligomerization, and nucleophilic addition. Well, you might say, okay, you have seen that in the Po Valley. How important is that on a larger scale? Well, I said that we see several fog events in the Po Valley, but here I'm reporting the map over Europe of frequency of fog days in winter. And as you can see, the Po Valley is actually not one of the foggiest places in Europe. We have several fog events, very humid condition here in Northern Europe. So potentially we have the condition in winter for the formation of the aqueous secondary organic aerosol. And also, we have the precursors. We have biomass burning emission. This graph shows the production of energy from renewable sources in Europe, starting from 2004 to 2013 from Eurostat. And you see that we keep increasing production of energy from renewable sources. And the biomass burning is these light blue rectangles. And as you can see, we are also increasing significantly the production of energy from wood burning, especially after 2008. And at the moment, the combustion of wood accounts for almost 50% of the renewable energy used in Europe. So we have the conditions and we have potentially the precursors. So we tried to calculate a rough estimate of the aqueous secondary organic aerosol budget over Europe. We used the wood burning black carbon emission estimated for Europe, which corresponds to 0.1 teragrams per year. We used the aqueous aqSOA to black carbon ratio measured during this experiment in the Po Valley, which vary between 1 and 5. So we can say that roughly the aqueous aqSOA budget can range between 0.1 and 0.5 teragram per year. You might say, okay, what is that? Just to give you an element, a term to compare, we can say that we know that in Europe, the budget of primary organic aerosol emission is 2.5 teragram per year. So this source of organic aerosol is actually comparable to about 20% of primary emission, so should not be neglected. Okay, I said this kind of source, this kind of component of organic aerosol is important for air quality, but might also be important from a climate point of view. In fact, most of the model, the climate model, treats organic aerosol as a purely scattered component. Organic aerosol is white. Okay, so one way to define the ability of an aerosol component or an aerosol population to absorb solar radiation is the absorption angstrom exponent. I report here just the formula, but anyway, in a simple way, the absorption angstrom exponent for a population of aerosol, which is dominated by soot, is around 1. When you have an aerosol population dominated by biomass burning organic aerosol, the absorption angstrom exponent is about 1.7, sometimes 2. And then for an aerosol population dominated by dust, the angstrom exponent is higher than 2, actually, about 2. We measure the absorption angstrom exponent during the experiment in Bologna, so where we observe the formation of aqSOA in the wet aerosol. Here I report for Bologna the absorption angstrom exponent versus the fraction of aqueous aqSOA, and points are color-coded as a function of the fraction of biomass burning organic aerosol. So here is the way we can read this graph. If we have a negligible aqueous aqSOA formation and the organic aerosol is dominated by fresh biomass burning emission, the absorption angstrom exponent is about 2, as we expect from literature. But then when the aqueous aqSOA concentration increases and also the contribution of fresh biomass burning decreases, we go towards blue points here, the angstrom exponent can be as high as 5. So this means that the absorption Armstrong exponent of the aqueous SOA is much higher than fresh biomass burning emission. We were also able to measure the absorption Armstrong exponent of the aqueous SOA in fog water. So we took the fog water samples, we record the absorption spectra in the UV visible region, we measured the absorption Armstrong exponent, and it ranged between 5 and 9. So we can definitely say that the aqueous SOA can actually contribute to the absorption of UV and visible region. So it can actually have a role in climate change, in climate warming, actually, in this case. So to conclude, aqueous SOA from wood burning emission is potentially important and an accounted player, both in our quality budget and also climate force imbalance. Regional and local air quality models can actually better support environmental policies, taking into account the formation of secondary organic aerosol in the aqueous phase, both fog water and aerosol liquid water. But future studies are needed in order to better constrain the chemical mechanisms responsible for the aqueous SOA formation, and also to identify the precursors of this SOA, because we need this kind of information to be implemented into models. And all this data just published last Monday. So these results are now available on PNAS online, so it's available to everybody for free. But if you have further questions, you can definitely talk to me now or contact me by email. And with that, I would like to thank the funding agencies for this work. So all the environmental protection agencies of Northern Italy, but also we have the contribution of Aerodynamic Research, the Finnish Meteorological Institute, and the Joint Research Center. And I would like to thank also all colleagues from CNR, University, the Environmental Protection Agency, Harvard College from Los Angeles, and Aerodynamic Research. And I would like to thank you for your attention.
Thank you very much, Dr. Gilardoni.